Hi there. Have you ever wondered what actually makes up an agent? And which components are absolutely essential? We definitely need a brain, which is large language model. Plus, some knowledge is essential. In simple terms, a prompt. But does that already give us an agent? No, definitely not. These elements might help you build a chatbot, but there's something essential that's still missing. Something absolutely crucial. The missing piece is the tools. They are what make the agent, allowing it to interact with the outside world. When you connect the LLM, knowledge, and tools through an agent loop in your program, you create an AI agent. But let's take a moment to look at the components from the data processing side, to make sure we're all on the same page. From the user's point of view, the most important part is the front end. That's where they enter questions and receive answers. Then there is the agent, which is a program you create using the ADK, and which implements the agent loop. The agent calls the large language model, which is the brain of the entire operation. I'll take an example from previous lessons, namely the storyteller agent, to see how the data exchange goes. The process begins when the user requests a story. The front end then sends this request to the back end, specifically to the agent. The agent packages this message with extra details like the agent system prompt. It also creates a formal structure to clearly indicate who made the request, essentially formatting it in a way that makes sense to the language model. Then the agent sends it to the language model, which prepares the story and sends the information back to the agent. The agent filters out any information that's not relevant to the user and sends the story to the front end. And that's basically the whole process for one agent loop iteration. But as I said, for me it's more of a chatbot. So let's consider an agent that uses tools. A very simple one. Let it be a calculator. I'm going to equip this agent with two tools. One for multiplication and another for addition. Obviously, using an agent as a calculator isn't the real-life example, but it'll help you grasp how the tools function. Imagine a user asks the agent to add 7 to 8. The request is sent to the agent, and just like before, the agent wraps it with extra details, like a system prompt and formatting. But there's something extra. It includes information about which functions the agent implements that the LLM might potentially use. Then the whole thing is sent to the language model, which can either respond to the user or decide that it needs to use a tool. Just like in this case. The model sends a message to the agent, and the agent performs the addition requested by the model. Then it sends the entire message history back. The language model can choose to use another tool, or decide it can handle the user's question by itself, like in this situation. Then, the response is sent back to the agent. If the agent sees that it's not a tool call, it processes the response and forwards it to the front end. And that's the whole process. I hope this is clear to you, because now I will implement it in practice. If you watched the previous episodes, I'm using the same environment. I go into the folder, activate the virtual environment, create an ADK agent from a template. I'll choose the model later. As usual during this step, a folder with my agent's code was created. That is a calculator. In the .env file, I've already entered the Gemini API key that I'll be using. Details are in the first episode. You already know the agent.py template really well. I'm going with the Gemini 3.5 Flash model because it's both super fast and really capable. Naturally, I need to include the description and instructions that are used in the agent system prompt. I'm specifying tools explicitly. I already have a prompt. Now it's time for tools. In this case, the tools are simply Python functions. The first function is addition. While strict typing is not required in Python, type hints are a very good practice. Right below the function definition, I include an essential element, the docstring. This should contain the function's documentation, clearly outlining what the function does, the parameters it takes, and possibly what it returns. It's important to approach this with the same attention to detail as you would when crafting a prompt for the agent, because in fact this documentation is essentially part of the prompt that affects how the model interprets and utilizes the function. Now I need to return the result of the calculations. It's really straightforward. And that's all. The tool has been built. No decorators are needed as in some frameworks because ADK can inspect the function, which in Python is not that difficult. I'm defining multiplication in the same way. Basically, these two functions are almost identical. The description is a bit different, so is the operation on the returned value. My advice: when you're writing function descriptions, imagine how you'd want someone to explain them to you, but keep it concise and avoid unnecessary redundancy. There is one more step left. I need to add a list of tools to the agent definition. This is simply an array containing functions. Not that complicated, right? Let's check now whether the agent works as intended. As always, I'm launching ADK Web because it offers an outstanding visual interface that allows us to observe many aspects of the agent execution. This is very important in this case. As you can see, the calculator agent is selected, so I can ask for calculations. What's the result when you add 7 and 8? Wow, that was lightning fast. On the left side, you have the agent structure. There's a root agent and two tools, addition and multiplication, just as I defined in the code. Let's now see what these symbols in the chat mean. Add with a lightning symbol is a tool invocation. The one with a check mark is the result of the call. The last position is obviously the final result. Let's take a moment to look at the trace. Please recall the data flow I showed at the beginning of the episode. You see two large language model calls here. As a result of the first invocation, the LLM requested the execution of the addition tool. Calling the tool didn't take much time, just as expected. Based on the output from the function, the large language model prepared the final response for the user. It was during the second call. Let's now look at more technical data. What exactly was sent to the large language model and what was returned? This is the first query to the LLM. It is clearly visible how ADK constructs the system prompt from the agent's configuration, combining description and instruction. For you, however, function declarations will be more interesting. The first one is the addition function. Here we have a description taken directly from the docstring. Next is the specification of the tool parameters. We have variable names along with their types. It is also clearly indicated which parameters are mandatory. Exactly the same pattern you can find for the second function. Then there is the user's query. And exactly this whole information in JSON format was passed by the agent to the LLM, just as was shown in the flow at the beginning of the episode. Let's now look at the model's response. It didn't send anything that could be passed to the user. Instead, we have a function call. The model wants to perform addition, and the parameters are the numbers 7 and 8. That's the end of the agent's first request to the model and its response. Now let's check out the second one. Longer communication with language models works by sending the full conversation history each time. That's also the case this time. At the beginning, we have a system prompt with a function declaration, a user question, and a request from the language model to the agent to perform the addition of the numbers 7 and 8. Then the communication returned to the agent, that is to my Python program, which performed the addition and sent the result with the full history back to the model as the second query. Note that the output of the function has been wrapped as the result. Now let's see the model's response. It is very simple, just a single sentence with the result of the addition, which was ultimately passed to the user's front end, and that is exactly the entire process the agent went through. I hope this makes sense to you now, or will become clearer soon. If not, don't worry. Everything will surely make more sense over time. Let's now take a look at what's important for implementing effective tools. First things first, make it clear. This applies on many levels, and there are several important aspects to consider. It's important to give functions and parameters names that clearly explain their purpose. Similarly, keep descriptions in docstrings concise, yet complete and easy to understand. While you're not doing this for a human, imagine someone looking at it for the first time. They should be able to grasp what it's about. When you're returning value, it's best to give it a clear structure. Wrap with dictionary. For instance, when it comes to errors, make sure you specify that it's an error and clearly describe what it's related to. Instead of providing just an error code, offer a detailed description of the problem. Keep it simple. This is important not just for smaller models, which often get confused with complex function calls. Try to keep function calls straightforward, with a limited number of parameters, ideally using simple types for those parameters. Think about parallel execution and optimization. The tools I've set up are simple and run really fast, but that might not always be the case. It's a good idea to think about whether the agent might need to use several tools at once. In that situation, programming them to work asynchronously can save execution time. Let's take another look at my agent and see where these tips could potentially be applied. I'm not going to edit the function descriptions since they're simple. Instead, let's take a look at the return value to ensure it's structured as a dictionary. In this case, it won't make any difference because simple types are automatically wrapped in a structure with the result key. However, in a different scenario, it might look like this. I should definitely change the function's return type to a dictionary. Now let's change the same thing in the second function. Just remember that this is a formal action, because it actually doesn't change anything since the result key is returned automatically anyway. I have an idea for a more practical example. So, I will define a function called divide. The value of my return dictionary can be a number or text. You'll see why in a moment. Division is not much different from other operations, with one exception. It doesn't always work. Of course, you can probably guess that it's about division by zero, which is not possible. I'm going to handle this exception directly. If the denominator is 0, I'll return an error. The error will be in a dictionary, with the value as a string. It's why I've defined the return type of the function that way. In every other case, I'm returning the result of the division, also as a dictionary. I hope it's now clear why returning a value as a dictionary is more practical, and it will become even clearer when you have to return several values at once. To make the tool work, you'll need to add it to the agent's definition, within the tools array. At this stage, it's worth mentioning optional parameters. They're a standard feature in Python, and are also used in tool handling by AI. I'm adding a parameter c to the add function as the third number, with a default value of 0. I need to update the docstring too. The calculation formula also needs to be updated. It's important to note that parameter c is optional. The language model can include it in the call or choose to leave it out. But I'm reverting this change because I'll need the original version of the function in my next step. I would like to focus on designing applications with parallel tool execution in mind. Even in this simple example, I can potentially simulate how this would work and what to consider when designing functions. The first thing I do is a request for parallel tool invocation. My tools are very simple and execute fast. However, to simulate something more complex, I'm adding a 1-second delay to the function. This way, it will be easier to observe parallel execution. For parallel execution to work, the tasks need to be specific and independent of one another, but I'll figure something out. When you're adding 4 numbers, the parallel approach is to break it down into 2 separate tasks. Start by adding the first number to the second and the third number to the fourth. Once you have those results, simply add them together. And that's exactly what the model decided. You can see that the addition tool was invoked twice during the first step. Let's look at the session. It doesn't differ much from what we saw earlier. Of course, the user's question is slightly different. Of course, the more interesting is the response, where you should see a parallel invocation of tools. Here the model requested to add 1 and 2. But you also have a call to add 3 and 4. The same is visible in the main chat window. 1 and 2, 3 and 4. As a result, you get 7 and 3. So the next call is the sum of 7 and 3, which ultimately gives a result of 10. What you'll probably find most interesting are the traces that show the execution time for each element. Notice that the first iteration of the loop took less than 4 seconds, of which 2 seconds in total were spent on 2 addition operations. So the tool calls were responsible for more than half of the time in this process. Why weren't these operations done simultaneously? Well, that's because the agent is a single-threaded Python program and needs to run these tasks one after the other. But don't worry, it can be optimized. I'll show you how in just a moment. Then you also see the sum of both results, which takes a second. Luckily, ADK supports making asynchronous calls to functions related to tools. In many cases, the program spends most of its time just waiting, whether it's for data from the disk or for network communication. By converting a function to be asynchronous, you can significantly optimize the overall execution time, as it allows tasks to run largely in parallel. That's why I import the AsyncIO module and change only 2 things in my function: adding async statement to my function definition and altering waiting from synchronous to asynchronous. And that is absolutely everything that is needed to change the agent's behavior and achieve parallel tool execution. Let's test if that's true. I'm restarting the agent just to apply changes in code. I'm asking the same question to get exactly the same result, and what's more important, exactly the same tool calls. Just like before, we have the sum of 2 addition calls, followed by adding the results together, so the behavior remains the same. What's changed is the duration and execution of functions. Both addition function calls are now made simultaneously, so together they only take 1 second instead of 2. This is, of course, an ideal case of parallelizing operations, and in real-life scenarios, the benefit might not be as noticeable. However, it clearly illustrates the path to optimization. Keep in mind that the quicker the tool calls, the shorter users' waiting time. I think we'll wrap up today's episode here. I know we haven't covered everything about tools, but as you can see, it's a pretty big topic. Let's explore some other areas related to tools. Here, you've got an ADK agent equipped with local tools in the form of Python functions, which was our main focus today. But where else can you find tools? You can use a local subagent as a tool, and you can also have a local MCP server that offers a set of tools. However, the MCP server can also be located remotely, allowing for communication via TCP/IP. Additionally, there's the whole topic of long-running tools to consider. You can also find tools on the language model's side. After all, LLMs are evolving into agents rather than just being plain language models. For example, they offer grounding or executing Python scripts. Sometimes you'll want to delegate the implementation of a specific tool to the front end, because that's where it fits best. You can see how broad the topic of tools is, which is why it's impossible to cover everything in one short lesson. But if there's interest, we have plenty of topics still to explore. May your agents always use tools wisely and efficiently. See you next time.